Hello? Okay, there we go. This is a little bit simpler technology, so less room for it to go wrong. All right, so hey everybody. Thanks so much for being here early in the morning. Thanks for coming to the first talk. That's not always the case that you have everybody here. So my name's Monica, and I work at a company called SumUp, which is based in Berlin, but has offices all over the world. And today I'm going to be talking about building resilient front-end architecture. Specifically, some of the things that I've learned being at this company for the last 4 years and watching us grow from 80 people to more than 1,500 people today. So without further ado, let's get started. So the question I want to start out with today is, why do we rewrite software? I don't know about you, but in my career, I have rewritten the same code so many times. And sometimes the reason we rewrite code is for pretty good reasons. Maybe the spec of the feature has completely changed. But I think a lot of the time we end up rewriting code that may or may not really deserve to be rewritten. Or maybe we made mistakes early on, and that's what kind of doomed us to need to rewrite this code. So there are a couple of different explanations for why code is often in need of a rewrite. I want to start by sharing with you my first ever experience rewriting code as a software developer. So my first tech job, I was 19 years old. I got a job. My title was student webmaster. So it was a really cool job, as you can imagine. The title is amazing. You are both a student and a master at the same time. I mean, way cooler than senior developer or whatever job title 19-year-olds have these days. And when I came into this job, I had been writing PHP in my bedroom for like the last 4 or 5 years, so I thought that means I have 4 or 5 years of experience. And yeah, I came into this job and I inherited an existing project. And that project was written by the previous student webmaster. But the problem was that this code was written in object-oriented PHP. And I basically knew how to write the kind of PHP where you have a template and you make SQL queries in that template. So yeah, I had this project, and you can probably imagine what I decided to do with it. I decided to rewrite it, of course, because I just didn't understand this code. And I was like, well, I have to rewrite it. What is this with these, arrows and things like this? Very confusing. I didn't know anything about object-oriented programming at the time. So at the end of the day, I think a really big reason why we end up rewriting code is just because we are sometimes inexperienced. We don't put in the effort to understand what the code is doing, why it was written that way in the first place. Instead, we just say, well, I don't really understand it, so I'm going to rewrite it. I think another big reason why we rewrite code is because it's just fun. I mean, how many of us rewrite our blog static site generator every Christmas? Am I the only one? I mean, I maybe post 2 articles the whole year, but I spend my Christmas break migrating it, right? So that's cool, and unfortunately, it depends on your perspective, we also do this at work sometimes, let's be honest. Another reason why software gets rewritten is because finally there is a better solution available. As you know, on the front end, oftentimes we have to kind of hack things together to get it to do what we want to do because the platform was just not made for it. And eventually, slowly but surely, we have some kind of support from the platform. But perhaps the biggest reason why code gets rewritten is this one explanation that when you ask a developer, why do you need to rewrite this code, it's the one they're going to give you. This code is technical debt. Technical debt. This is probably my favorite thing that developers tend to use as a reason why the code has to be rewritten. But what exactly is technical debt? I think if I were to go in this room and ask you all, what's your definition of technical debt, and give me an example, I'd get a whole lot of different answers. For a lot of people, it might be code I didn't write. That code is technical debt, maybe because I don't understand it. It could also be code I wrote before I knew what I was doing. This is definitely the case for me. I've been at my current company for more than 4 years, so I have a chance to really look back at code I wrote before I knew what I was doing. For some people, it can be old libraries. Things are changing all the time. Maybe the fact that you haven't updated is slowing you down. It can also be seen as features that nobody's using, right? Because we love migrating in JavaScript. So yeah, those features that no one uses are still things you need to kind of pull along with you as you make those migrations. So if I were to sum it up and kind of, say for me what I think technical debt is, I would say it's code, tools, or infrastructure that negatively and repeatedly affects the speed or quality of delivery. Now, what does this look like in the real world? It kind of looks something like this. I start adding new features to my application, it's very fast, and over time it becomes very, very slow, right? It's very painful, and you're just sad every time you need to touch that code base. Now, what's worse is this pattern, often begins like this. You start a new project, it gets slower to add new features over time, and at some point you say, okay, I just can't live this way anymore. So you make an impassioned plea to the product manager or to your tech lead or whoever it is, and you say, guys, I need to refactor this code. So then you think, amazing, I finally understand how this code is supposed to work. So I'm going to do it right this time. I'm going to do what the guy who previously wrote this code didn't know when they wrote it. But unfortunately, it often slides right back down, right? You think you know how to do it, and in reality, you end up oftentimes with a solution that is even worse than the original one. And I like to call this recurring technical debt, or technical debt on a subscription model. It's like, okay, how can I cancel this subscription? I keep rewriting this code, and it gets worse. And what's more depressing is that there is like an official technical term for this. It's called the second system effect. Maybe you've heard of it if you've read the Mythical Man Month. And in short, this is our tendency to take code that works, that actually is not so bad, and then we replace it thinking that we're gonna finally solve the problem, but in fact that code is even more complicated, over-engineered, etc., than the original solution because we have too much confidence. Now, there's another great quote about this by the creator of C++. He says, legacy code often differs from its suggested alternative by actually working and scaling. So yeah, I don't know about you, but I find this super depressing. It's like, okay, I end up with technical debt, I try to fix it, and then I make it worse. And this happens a lot of times. I kind of feel like this, the snake that eats its own tail, And you have to wonder, is this just my destiny as a programmer? Is this something that I am doomed to do over and over again? Because the hard fact is that the real cost of software is not in the initial development of that feature, but rather maintaining it over time. So for me, the question is not why do we rewrite software, but rather how can we make our systems that we are building more resilient to inevitable change? So instead of having a situation that looks like this, where the speed of adding new features dramatically diminishes over time, we actually end up in a situation where we begin to accelerate the speed that we are able to add things to the code base because we have some kind of foundation there that is going to make it easier to do. So how do we reach this amazing place where your code base actually feels somewhere very productive? Well, the answer that I have for you and that most people will have for you is perhaps not the most satisfying. It's good architecture, right? But when you see this, you're like, oh, really? That was like, not the answer I was hoping for, because it's so abstract, right? You just kind of roll your eyes like, well, thanks for that. That was mind-blowing. Congrats. Now, why is it that good architecture just kind of like leaves a sour taste in our mouths? I think architecture has become kind of a dirty word. It sounds kind of elite when someone says, I'm an architect. And then for a lot of us, maybe you've never worked with a software architect before, or maybe you kind of don't really know what they do. We know that software architects have kind of like transcended coding, but what they do after that is not completely clear. And when you think about it, in front-end, let's say, we haven't even come to a conclusion about whether Flow or TypeScript is, the way to go. But just imagine the entire software development community trying to agree on a definition of software architecture. We just don't have one. Everybody disagrees about what software architecture really is. Does the language that you are using count as software architecture? Some people say yes, some people say no. And at the end of the day, it feels so detached from daily problems, right? As a front-end developer, my task, for example, is to change the behavior of this button, right? And for whatever reason, the person who was working on this code before made it so difficult that I could change how that button is working, right? So when you say, well, good architecture would fix that, it's kind of an unsatisfying answer. So instead of trying to say, all right, I'm going to redefine architecture, and finally, at this conference, in this talk, we're going to agree on what software architecture really means, I want to kind of reframe the discussion and think a bit about architecture as enabling constraints. Now, I learned about this term not too long ago, and I thought it was a really apt metaphor for architecture. The reason for that is that a lot of times architecture is about limiting what we can do as opposed to giving us more capabilities. So we're going to talk about specific constraints, how we use data and code, that can help us to move faster over time. Now, if enabling constraints sounds a little bit, let's say, abstract, we can look at an example of this in real life. So imagine you're driving a car. Now, in Germany, which is where I live, we have the Autobahn, right? Now, as an American, I find it rather horrifying that on this street you can drive in some places without a speed limit, right? The only limit to how fast you can drive on that road, is the speed at which your car can safely travel. Other than that, it's completely free reign. But why is it that this doesn't end up in a fiery crash every single day, with cars piling up on each other because they were going too fast? Well, I think a big reason for that is because we have some constraints in place, right? We have our roads, we have barriers between cars that are driving in different directions, we have lanes, we have some behaviors that we use in order to keep things orderly, like how we change lanes. We use the turn signal, for example. And in a lot of ways, software is very similar to this. We put in these kind of constraints in order to be able to move fast, but also in a safe way. So I want to look a little bit on how this has happened in programming as a whole in the past years. So we started out with object-oriented programming, let's say. Not at the beginning of time, but relatively recently. And in object-oriented programming, we kind of gave away some of the powers that we previously had, where we could just structure our application however we wanted to, right? That was the power of GoTo. But we decided this is considered harmful, right? And instead, we decided to organize our code into classes. And while this was a constraint on us, it actually enabled us to separate the way that our code is structured and the way our application is structured, giving us independent deployment of subcomponents. Now, similarly, perhaps in a paradigm you're more familiar with, we have functional programming. Now, functional programming takes away a whole lot of capabilities, right? But perhaps the biggest one is mutable data, right? Strictly speaking, mutable data is more powerful than immutable data in the sense that you can just do more with it. You have more options. But in reality, when we give away our ability to mutate data, we eliminate an entire class of problems, right? The situations where two different things want to operate on data at the same time, and they end up having concurrency issues, right? And as a result, we said, okay, I don't really need to do that. I'll give away this control, and instead, I'm going to get something much more powerful in return. Now, this has also happened, I believe, in front-end development. There are tons of powers and capabilities that we give away in order to be able to move faster and more safely. Let's start with an easy one, var versus const, right? We said, I don't really need to be able to reassign the value of this variable anymore. And because of the fact that we gave this away, it's so much more predictable to read the code that you are writing or the code of your colleague. Because you know if I declare this with const, it's not going to change wildly over the course of the function. Or what about moving from jQuery to React? Strictly speaking, okay, jQuery, I mean, it gave you this really kind of low-level way to work with the DOM, right? You kind of had to do DOM surgery, super imperative, in order to be able to get things done. And we said, okay, I'm going to give away this DOM manipulation. I'm going to stop doing that. Of course, you have escape hatches, but the fact that we gave it away meant I can finally test my user interface in a reasonable way. I finally have something predictable. Now, the last one I want to talk about is a little controversial. I don't know if it's just the people I follow on Twitter, but like every few months there is like a cyclone of controversy about this one, CSS in JS. Now, I don't want to take a hard stance on this. I've been using CSS in JS for about a year now. And one thing that I have really noticed is that it forces me not to rely on global side effects, right? Because CSS is very global, and the fact that I can kind of contain that means I have a lot more safety. So it enforces that I don't rely on these side effects anymore. The point I want to make here is that we are constraining ourselves all the time. We are looking for ways to stop doing all the things that we can possibly do. And we do that because we want to trade those constraints and those powers and capabilities that we give away for things that are more important, such as safety and speed. So today I'm going to talk about 3 specific constraints that you can apply to the applications that you are working on that are going to make your application more resilient. Now, I should mention, this is not exhaustive, right? There are tomes written about software architecture, and these are just 3 specific ones that I have found especially useful over the last year or 2. So we're going to start by talking about the constraint, and then we're going to talk specifically about what it enables for us. The first one comes down to source code dependencies. I think a lot of times developers focus a lot on how should my directories be structured. Now, that's nice, I guess, if you cannot search through your directories. But in reality, what does the directory structure really tell us about how the application is organized? So let's talk about why source code dependencies and the direction that they work in is important. As you might know, there are a couple different ways we can organize the internal dependencies of an application. Perhaps the most famous and the most dear to our hearts, the most familiar, it is the big ball of mud. Yeah, and so in short, if you don't have any rules inside the application you're working in on what is allowed to import what in your application, there's a very high probability that you're operating in this big ball of mud. Yeah, so that's an interesting option. It's a very natural option, but what alternatives do we have? We also have a layered approach, right, where we have strictly defined layers in our application, and they need to be imported in a single direction. And finally, we also have a modular approach. Now, I think a lot of people might say, well, my application's modular. And the bad news I have is that just because you have modules doesn't mean it's modular. But when I talk about modular here, I think of something more like a monorepo style where you have strictly defined APIs or micro frontends. But we're not going to talk too much about that. We're going to stick to the first 2. So the question is, what's the big difference? Why should I actually care what in my application is allowed to depend on something else? I mean, don't I just want to reuse everything? Well, think about what happens when something changes in your application. In the big ball of mud, what side effects could this possibly have? Well, it can have every side effect, right? It can touch anything. You have absolutely no way of knowing or reasoning about what has changed. You can make a very earnest promise to QA, that your change has only affected one area. But we all know how that turns out. You violate that trust once and you'll never get it back. So the fact is, you have a huge or an unknown scope of potential regression in your application, and this oftentimes leads to cross-team conflicts, right? Because nobody likes to get a bug report that somebody else caused, right? But this happens all too often. Now, what about in a layered approach? When something changes, what are the results of that? Well, the interesting thing is that you can actually draw a boundary around what has changed in your application. So you know this is the potential scope. And usually, you're able to define your architecture in a way that it kind of reflects the structure of the teams working in that app. So you can ensure that you're not going to be affecting other teams. So this is really the key difference between having this big ball of mud and a monolith that is still well organized from an internal standpoint. It comes down to the internal dependencies. Now let's look at a more specific example of how this could look in a typical front-end app. So imagine that you have something like this. You have your router, you have some kind of separated API and data layer, you have your user interface, and your business logic is somehow extracted from this. Now, the important thing is that these sections of your application, these pages that you have or subsections, they ought not to really know about each other. In an ideal world for each of these pages, the rest of the application may as well not exist at all, because that's how you can ensure that changing something in one place is not going to affect things in another place. And the result is that it is so much easier to isolate the impact of changes. But you might have a question on your mind when you look at this diagram, and that is, but Monica, what about shared components? Because as front-end developers, we love to share components, right? When we create a component and we make it shareable, we feel like we've done our duty as a developer. You know, you can go home at the end of the day and say, I made a reusable component, and it feels like morally good, you know? But I have a bit of a kind of radical opinion on this, and that's that shared components belong in one of two places. They either belong in a design system where you have all of your business logic free user interface components strictly defined, changing at a different and slower pace than the rest of the system, or it's probably a good idea to copy and paste those components. Oh my God. We're going to go deeper into this next. So the next constraint I want to propose to you guys is being more conservative about code reuse than we have traditionally been led to believe is the right way to go. Let's see how you like this one. So as developers, we love dry, right? We love the feeling of extracting common code, putting it somewhere, and the total maybe number of lines of code is less, and we feel really good about that, you know? Like, you feel like you've done a good deed in the world when you create these kind of extracted functions or these general components. But what's often the result of actually doing that? Many times we end up with code that is very brittle or code that results in a lot of side effects. And we do that because we say, well, it's code reuse, so therefore it is automatically the right thing to do. But is it really? I think it's important to consider the impact of time on shared code. Now, imagine you're building a new page in your application, and it needs a component. And you spot a very similar looking component on another page. What is your first instinct? Your first instinct is to say, well, if I'm doing it right, the right way, I'm going to take that component on the other page, I'm going to generalize it a bit, I'm going to stick it in this shared directory, and I'm going to make both of these things import that new, wonderful, generalized shared component. But what actually tends to happen is that now these two pages are inextricably tied together. And over time, what's interesting is that this component kind of wants to make a mitosis, like a cell, you know? It kind of wants to divide because you see two competing use cases appear inside of this component. but the magnetism of being in the shared folder makes it very, very hard for them to separate. And you notice that they kind of want to separate with hints like if statements, or I need to understand the context of where this component is used, right? This component has an existential crisis every time you render it. Where am I in the app? You know, and what should I do? And the interesting thing is you end up with a component that is not actually general anymore, but extremely specific to those two particular cases. And the end result here is that you create a situation where you want to change something in one place, and it's very likely to have side effects somewhere else. So the point I want to make here is that it is so much more important that our code remains decoupled than it is that the code remains dry. And that's because code reuse is not a goal in and of itself. Why do we try to make code reusable? The main reason for this is that we want to have as few bugs in our code as possible. And we know that having less code is maybe less chance for bugs to creep in. But here we're actually introducing more possibility for bugs by making code reusable in a situation where those things tend to diverge over time. Now, I saw this really excellent tweet, which summed it up perfectly for me. It says, a regular person sees a glass as half full or half empty, but the engineer sees both and learns in what context it makes sense to see it half full and when to see it half empty. Now, the takeaway here is that sometimes you just need two glasses, right? Sometimes two people need to be able to drink water without knowing that the other person is drinking water too, and if you change the liquid, nobody cares. So, as a result of being a bit more conservative about what we decide to make reusable in our application, we can avoid coupling together code that is likely to diverge over time. Finally, I want to talk about enforcing your boundaries. Now, oftentimes what I have seen happen is you have a meeting with all of the developers working in an app. And this is maybe called the architecture meeting. So you go into this meeting and you all agree on what is the target architecture for the application you're working on. Amazing. Maybe you even document it because, you know, we love writing documentation that other people may or may not read as developers. So we write this documentation, maybe we make a really nice diagram and we put it in the wiki to collect dust forever. Because I can guarantee you one thing. There is no developer that when they start to write a feature is gonna go into the wiki and try to find that architecture diagram and make sure they are compliant with it. It's just, I mean, it's not human nature. So you can spend as much time as you want making those discussions, documenting them, but the reality is someone wasn't in that meeting, or someone was hired in the meantime and maybe missed that page, and then their first pull request is going to disappoint you. So if we can't rely on documentation entirely for having our architecture be enforced, what can we do? So let's imagine a specific scenario. I'm writing my app, okay? I see that I have kind of a ball of mud happening here, and I want to, you know, snip my cross dependencies, and maybe I have a little bit of business logic. And I say, okay, I'm going to do a small amount of duplication to keep these things decoupled, and over time, that bit of business logic probably specializes a bit to the context in which it is used. Now, what happens when that new developer, or that developer who wasn't at the architecture meeting, comes into the code base and see these very similarly sized circles? They look at it and they get this euphoric feeling inside of their chest, like, I can extract that, right? I mean, it's like, you know, you see it and you have this physical reaction, like, oh my God, I can do something good for the world today. And the question is, how do we stop them from helping us, right? Because they think it's the right thing to do. And you're just like, please don't do that. How can we prevent this, you know, good behavior in your mind? So there is a really awesome tool called forbidden dependency tests, which you can use. Now, the way you can think about this is you have normal tests, right, that assert the way that your application is going to work. But you can also write tests that assert the structure of your application. So what is allowed to depend on what in the context of your app? So one specific example. Let's imagine that you have two separate pages, and you want to make sure that those pages don't depend on anything from the other page. What you can do is make an assertion that this subtree, where the page lives in the directory structure, may not import anything from anywhere else except its own subtree, or nothing is allowed to depend on me. So I write a page, I can say, no one is allowed to import my code. That's pretty cool, because you can actually define what behavior you find acceptable for other people in an automated way. And you can put this into your CI as something that's going to run every single time people push code. Now, this concept of forbidden dependency tests exists in other languages. I did not find very many options in JavaScript, but there is one called Dependency Cruiser. If you are looking for something specific, it's the one that we are using. And to give you a bit of an idea, it works like this. It's extremely declarative, so you don't even have to really write tests, let's say. And you can assert anything that is not in that page is not allowed to depend on something else. So what's really cool about this is that you have an automated way to preserve this aspect of your architecture over time. And you can do this also gradually. In our application, I can tell you we don't have a perfect delineation between every single page, but it's actually something that we are monitoring and working towards. And I can guarantee you that until you have set up an automation like this, you have no idea what is happening in that app. You have no idea what kind of things people have done in the past, what they are using, what kind of dependencies exist, etc. So I would really encourage you to have a look at this and see how you can use it in your world. So I want to recap for a second. What have we learned today? The first thing that we talked about is the hard fact, that the real cost of software is not about implementing the initial feature, but about maintaining that feature. Because more often than not, it's gonna change, right? And you need to find out if you can avoid having to rewrite that entire feature every single time a change in requirements is introduced. The other thing is that architecture is about applying enabling constraints. It's not about, let's say, just putting in structure to the application, but how can you constrain what things developers are going to do in that app so that you're able to move faster and more safely over time. And at last, there are really small changes that you can make to gradually adapt the architecture that you're working in. The first one being, think in a directional manner. If you don't want to end up with a ball of mud where everything can affect anything else, we need to think in a layered application approach where we know what is allowed to talk to what. We also want to be a bit more conservative about code reuse, because oftentimes code reuse ends up in coupling. So we just need to be mindful of that. And finally, we can enforce our boundaries. It's not just about having, that one-off architecture meeting where you create one diagram and it's going to end up never being read by someone else. We can use automation and CI to make sure that certain aspects of our architecture will actually be preserved over time. And you don't have to wait until code review, which is far too late to realize that something has gone wrong. So to wrap up today, I want to share just two main takeaways that I hope you internalize from this talk. The first thing is this. A lot of times when you talk about architecture, people immediately jump to thinking about things like frameworks or abstractions or design patterns, let's say. But the reality is architecture exists on the small and on the large. So every time you write a function or you decide not to, or you create another module, or you keep it where it is, this is also an architecture decision, and it requires the same amount of forethought, because you don't know how you're going to have to change that in the future. It's not really possible to predict. And the last thing is that you don't have to derive architecture from first principles. I cannot tell you how many times I have heard people saying, okay, I need to find out how I'm going to do my front-end architecture, which is an ironic thing to say given the title of this talk, right? But the fact is, a lot of times the architecture that we need is not specific to React or specific to front-end, but rather it's just software architecture, because there are certain things about software that are universally true. And so often we look for such specific solutions based on the tech stack that we are using. In reality, there are many other communities and programming languages that have been around for way longer than us, and they have tons of amazing resources. So I just want to encourage you that if you want to dive deeper into architecture and learn more about it, not to be afraid to pick up a book that maybe has code examples written in Java or C++, because we can still learn things from those different languages and different communities of practice. Thank you very much. And if you want to talk architecture, I will be around. So thanks.
We have 2 minutes and 40 seconds for questions. I mean, there was a lot to digest, so there must be something. Oh.
Question is, don't you think that there are some situations when you have a request to add one function, which is very easy to add with spoiling architecture a bit, and management or business requires you to do it fast, but for maintaining architecture it is best to make decision to rewrite right away a lot of stuff, and that this incompatibility in views between business and programmers is one of the biggest causes of all this big ball of mud. Like the business tells you add this function and you say, yeah, I can add it right now, but it will make code a bit stinky. But it's better to rewrite a lot, because this one new feature requires whole another level of architecture. But you don't do this, and you end up adding small pieces of code, which in the result creates a big ball of mud inevitably.
What was the question?
The question is, all your principles which you have given in your talk make sense, but how to deal with different views on architecture between business and software developers?
Well, I don't know if the business really has much of an opinion about the software architecture.
No, but in time. I mean, like when one feature is requested, and you said it's obviously that to add one button is very easy. You are given the task and you are given a day, for example. But you feel that you need to rewrite everything and it will take a week. Should you take a week, or should you add the button in one day and ignore it and then fix bad architecture?
I mean, I think it's a very contextual question. So it's a bit hypothetical what the scenario is. I think you have to define for yourself what kind of violations you allow. I think there are certain violations that you can simply say they're not worth it. Specifically when it comes to coupling things together that shouldn't be. For example, let's say you have two parts of your application, they're owned by different teams. So adding coupling between these two things should be a no-go, because the fact is you're going to introduce bugs and regression inevitably if you do that. But I think more often than not, if you set this up from either the beginning or you work there gradually, the cost of actually doing that is much lower, because you at least constrain the problem to an isolated area. So in reality, all software is kind of terrible, right? In the sense that you're going to have small messes in many parts of your code base, but the most important thing is not to allow them to become interconnected into a gigantic mess. So I think that's the most important thing to keep in mind.
Sorry, we're out of time. Let's say thank you to Monica.